So let me complete what I meant to do. I think this is problem 1.62, part D. It's not very difficult, but nonetheless, we talked about this, the area vector. Yeah? So area vector is defined to be dA, the integral over the entire surface, but there's a nice formula for it. Area vector is 1/2 the closed line integral of R cross dl. And what does R and dl mean? This is R, any origin, and dl. My version of the proof actually requires part E. So the chicken before the egg. Yeah? So in part E, what did I show? A cross C equals, I don't recall, I somewhat recall, but I want to get it right. C is a constant vector. Yep, this is a constant vector. So, what I'll do is I will show the following. This is what I will show. Well, how does that prove the result? So this is, again, this is what I'm going to show. Now I'll argue that if I show this, I have the result. Yeah? Oops, sorry. In that case, look at this expression, and so what will I have shown? I will have shown that, yeah, we already know that A cross C is equal to C dot R dl. So if I subtract these two, what will I have shown? I will have shown that A minus 1/2 R cross dl cross C is equal to 0. But this is not true for just one vector. This is true for any C. Correct? Which is the only vector whose cross product with every vector is 0. The 0 vector. Yeah? Cross product with every vector is 0. So this is for every C. Then we have the result. So this is what I need to show. Well, let me get rid of this. We have shown that this suffices. So what I'm going to do is, well, let me show this. So it's like a proof within another problem, because this is all there is left to be seen from because of part E. And I'll be taking cross products and using the inside cover, which you have with you today. Show of hands. 2 people paid attention. Well, I'm going to print it out, laminate it, tattoo. Yeah? So many options. Let me start with this guy, except I'm going to put the C over here, and then a minus sign I can fix later. So C cross R cross DL. I just took the C inside the integral. I'm not worried about the 1/2 at the moment. And I changed the order. That's fine. This is equal to negative of that. But we can put the negative signs later. And I have A cross B cross C. So when I have A cross B cross C, what can I do? I can use the back cab rule. Yep, that's one way to remember it. And so, again, you get 2 integrals. Back R, cab C dot DL minus, so now, so sorry, this is AC, BAC. Now cab, it starts with this one, so I have DL and C dot R. This is just the back cab rule, and I'll refer to this as equation number 2. Fine. Now look at this. I've already gotten one nice part. This part I don't have to worry about at all. I even have a negative sign. Remember, when I turn this around over here, I get negative sign. The only thing that is missing is this guy, but that's perfect. There's this guy. So this better be exactly the same as that quantity. Yeah? I'm going to run out of space. I write big and it's a small board. So I'm going to now focus on only this quantity. And I'm going to calculate this. Okay? So now, first of all, recall what is, we showed this before, yesterday. It's a odd way to write it, but if you have a constant vector, you can write this, okay? So all we're going to do is really vector relations and properties, just back and forth and back and forth. It's not difficult. You just have to try out several combinations till you get the answer to work out right. And you'll stumble till you use several ones and see which manipulation works out. I didn't find the proof particularly enlightening, but I didn't spend time reflecting on the proof. I got the proof and I said, let's move on. But maybe there's something deeper there, but it's not very exciting. It is just achieving a mathematical goal by simplification and manipulation of symbols. So again, I'm only going to worry about this term. So R C dot DL is, first of all, I'm going to write this as R. Instead of C, I'm going to write it as C dot gradient R dot DL, because this is nothing more than C. I'm just doing a substitution. So what I'm going to do, because I'm going to write over and over again, I don't want an equation just hanging in in the middle of the board. So at the very top, I'm going to write the goal. No, the other way, sorry. 1/2 R cross dl cross C is equal to C dot R dl, and what we have shown is equation 2. We already have this, and C cross R cross dl equal to R C dot dl minus dl C dot R. And this guy I'm calling equation 2. So now I can continuously write. I'm not going to mess with this. I'm going to leave this alone for a while. So then I have I'm going to start substituting over here. I'm going to use another identity, just a vector identity. None of this is tough. Gradient of C dot R. If I recall, Martin said this is property number 4 or something like that, right? And that is C cross the curl of R. The curl of R is 0 plus C dot gradient of R. So which I have over here. So I'm going to take this guy in this integral and replace it with that. So what I have, we're almost done. Like I said, there's no difficulty. At this point you're going, yeah, I see it, but okay. You know, that is the essence of the proof. So I'm replacing this guy with that guy. C dot R. That's a vector dot dl. This is a curious object, huh? So this is a vector. You're dotting with the vector. So this is a scalar. Then you get a vector over here. So you better get a vector on the other side. Perfect. This is also a scalar, another vector. Okay? So, and this is why I wrote all of this down, because now I can erase all of the substitutions. I'm going to look at this equation one component at a time. So let me look at the x component of these two vector equations. Okay? So the x component gives so the x component of R is just the x coordinate, and C dot dl, because that's a scalar, and that's equal to x gradient of C dot R dot dl. Yeah? Now, what I want to do is I want to take this inside. So I'm going to look at what's this guy. Well, that's equal to, first I'm going to take the gradient of this guy. Gradient of x is just x hat. And then I'm left with C dot R And then I'm going to pull the x out and take the gradient of what was there to begin with. And that is sort of what we need, c dot r. And this is what we have. So I get, I'm starting from here, x c dot dl equal to, I'm going to write this minus that. So I get dot dl and then minus this guy, c dot r. I'm going to get dl dot x hat. Correct? Sorry. We're almost done. Okay, I've been just cranking away. Are we good?
Your axis and cross product kind of look similar here.
Yeah. You know what? True. To be fair, x's and cross products do look similar.
Yeah, I made mine
I know.
smaller.
So the power of color coding. Yeah, x hat, you know it's x hat. Are we good? So it's kind of nifty. I think it's clever, but I hope it's right. I think it's right. Look at this guy. Correct? So it is color coded. Oh, this is dx, see? dl dot x hat. dl is what? dx, dy, dz. So it picks up dx, so I'm not going to put color code that one. What is this one? If you go all the way around a closed loop, remember? It's a closed loop. Yeah, you're starting with the same x coordinate and same position coordinate, and then you go all the way around the loop, and then come back, it is 0. And therefore, what we have shown is, for the x component, the mantra here is, what's good for the x component is good for the, what's good for the goose is good for the, good for the gander. Yeah. Oh, and here's my, so if I put x here, I get x there. If I put y here, what do I get? Y there. So conversely, so I put this. What does this mean? Similarly, yeah. Well, I don't care which component, so I'm going to put vector r, because it's just x, y, and z. And C dot dr equals minus, and there's that minus sign that gave us because we started with the, and dx becomes dl. Oh, not d, I never used dr, I used I think we're done, but I'll just insert it correctly to show it to you. But any questions? Component by component, it's true. It's true. So then, and that's this guy. So I come back over here. And this is the same as this. Correct? So 2 now becomes what? Yeah? So then I'm going to divide by 2. Then I'm going to bring the C to this side, and this becomes a positive. Doing it for many reasons. A, we use the result later, so it's good to have it, under our belt. B, just for you to see how these things are derived. Sometimes when you derive things, there's a meaning behind every step. Sometimes it's just a manipulation. But most often, if you reflect on the proof, once you have it, you can find meaning behind these steps. I haven't searched for it. I invite you to think about why this works here.
What do you mean, meaning?
It's a story, right? Yeah. Every proof is a story. It is not just a calculation after another. It is insightful. If you reflect on any problem for a while, after you have done it, cleaned it up, refined the notation, you'd go, oh, that's what I mean. The intangible meaning behind all of this. Happy? Everyone happy? Travis, you good?
Happy.
Everyone on the same page? That's more important. Happiness, kind of overrated. Same page, important. All right, good. We haven't done any physics, have we? You've taken cross product, dot product. You didn't sign up for a math major in this class, did you? Well, all that is about to change. And it's going to change beautifully. We're going to do physics, and it's just this over and over and over again. So that what you have seen actually will make sense because of the physical meaning behind it. Yeah? The statement for the delta function that I wrote gives you Gauss's law. So all of, these are the things that we're looking for. Okay. I sent you a couple of videos just to remind you what the electric field is. I hope you may have consulted a little bit of it. Okay. We'll be sophisticated. C-O-U-L-O-M-B. It's about the only word I know how to spell. So every chance I get to spell it, I spell it.
You told me you could spell
vacuum. Right, that's the other word.
So was that like the limit chapter model we just did?
Correct, yeah. Vacuum in Coulomb is V-A-C-C-U-M. I would have never.
No, you got it wrong again.
Did I?
It's 2 U's.
It is?
Yes.
Oh my God. Are you serious?
Yes.
Please Google it. I'm gonna, if it is, I'm gonna, oh no, I'm gonna delete it out of the video. So I know one word. Coulomb. Please tell me this is correct. Yeah, I would know vacuum if we were studying vacuum, because I would have read it 5 minutes before, and then I would know it, and then I would pretend as if I knew it all along. That is my game, you know.
Yeah, we were doing it in one of those 3 classes.
Yeah.
I think about you and Sam got it right the first time. Everybody else had 2 C's.
I must have looked it up. There's a little bit of art of subterfuge in teaching physics. You pretend as if you know too many things. You really don't. So, anyway. But, Ashik, you remember that?
Yes, I do.
Damn it, I should be careful what I say. So, there are several lessons to be learned about a simple Coulomb's force law, writing it in an E&M course. First of all, what creates a force is a charge, right? And 2 charges. So I'm going to consider one charge over here, and I'm going to call it Q. And I'm going to hold another charge over here. This is the one I'm holding, and this is the one I'll be measuring the force on that charge. So it's my charge, so I get to choose the symbol, and I'm going to call it Q, uppercase Q. But the most important lesson is, well, we have to locate every single object. Oh my goodness, I should have drawn the dot after I drew the line. I amuse myself sometimes. What do you know? Bad spelling, nearly straight lines. Sources are always located by a prime. So this guy is R prime. Where I'm calculating the force, today it is force, tomorrow it will be field. I won't care what I'm holding in my hand. I know what I'm holding in my hand. I only care about the background field. Yeah? So this is the field point because this is where I am. This is where I'm doing my experiment. Okay? The force on this object is created by this object. So the field point is always R. If I move my hand, this is what changes. If I move the charges, that's what changes. And this guy is the separation vector, R minus R prime. Yeah? And a little bit of notation. When I write this, what do I mean? Well, I mean this always, but literally I mean the separation distance. Oops, R minus R prime. Okay? And another vector that is important to us is the direction. The direction in which I can feel the force. Well, it's either plus or minus that. Okay? And this vector, obviously, it's a unit vector along this direction. And so the notation is so the force I feel is going to be, who recalls Coulomb's law?
K.
K. Well, and we'll talk about K. Okay?
Q1.
Q1 in our case, little q and
Big Q.
big Q divided by what distance? The separation distance between these two guys. So it is this squared. And what's the direction? R hat. And if Q, little q times big Q is positive, it's a repulsive force. If the product of these two is a negative number, it's an attractive force, meaning opposites attract. This is Coulomb's law written in our notation. You've been looking at these kind of objects all along, even when we wrote the delta function. Yeah? Fine. But unfortunately, in a physics class, you won't have just one charge. I mean, you will in physics 1. But instead, what will you have? Q1, Q2, many charges. Q3, and so on and so forth. So a nice way to write that is, and I can make this very clear, on Q. I'll write it two different ways. K, Q1, Q over, look at that. Oops. Yeah? Plus K, Q2, Q over R2 squared, R2 hat, K, Qn, Q over. I want to simplify my notation, so what I'm going to do is I'm going to do K, and I'm going to bring Q out, and then I'm going to write it as I equals 1 to N summation, right? But what does this mean? It means that you take Q, oh, sorry. What is K? Is it?
That came from the back, so cold storage.
Well, it's 1 over 4 pi epsilon naught. I'll get to that. But what's the numerical value? Is it 9 times 10 to the 9?
Yeah.
8.99 times 10 to the 9? Please check.
Is it going to be in the back cover?
No, because we don't use numbers in this class. This is just the first time we're just telling you what it is. And that's it.
Yeah, it's 8.99.
Okay, now let's look at the units. This is newtons. This is Coulomb, and meter squared. So K would be newtons meter squared over Coulomb squared. Yeah? Good. Very often, remember the delta function, you see a 4 pi. 4 pi just dangles about in the universe. Yeah? So it is convenient to define a 1 over 4 pi with another constant. Okay? That's just the definition. This guy is called the permeability of free space.
What do you mean by the free space again?
We'll study material science. We'll study what happens inside a conducting material or an insulating material. So it won't be free space, but it'll be in a medium. When we make a capacitor, we won't necessarily leave the inside between the parallel plates of the capacitor to be vacuum. We can insert materials in. And they won't be conducting, and so it'll have a different epsilon naught. And we'll talk about how to even calculate that. Permeability. I'm going to write this with great confidence. I don't know. Of free space. I'll end today, you've seen all of this before, perhaps not in this sort of a notation. I've also given you 2 videos of 2 problems. That'll make sense shortly. Watch those videos as well, okay? We won't calculate force, okay? What I would, in this class, what we would do is we would want to know what's at that point, except that doesn't depend on the charge we're holding, okay? So the electric field is defined by it's defined by this, but truly it's defined in the limit as Q approaches 0. Because if you hold a very large charge in your hand, and if you want to measure the electric field, you're disturbing the electric field around it, because the charge you hold in your hand carries its own electric field. But turns out that really won't matter, because this is limit Q approaches 0 of K Q QI I over I. It's going from 1 to n, divided by Q. So in practice, we don't have to worry about letting the limit as Q goes to 0. You just find the force and divide by the charge you have in your hand. Okay? The Q simply cancel. And just so that you get used to it, I can write it in several forms. Let me this time just write it as U. Why did I forget that? This is the expression for charges floating about. But sometimes, or rather, very often, you don't have single charges floating about. What happens if you have a blob? In fact, in general, these are the kind of charges you can have floating about. There could be single charges. There could be like a sheet of charge. There could be a current-carrying wire. And there could be a blob. Yeah? So we should have an expression that describes all these different cases. Okay? For that, what we will do is what we always do. Historically, this summation, first it's sigma, the Greek letter S, became, this, and people started writing it bigger and bigger, and then it became the integral sign. And so it is true here. What we will do, and you can clearly see that how it evolves, in general, it becomes, I'll break it into several components. I will write it as K this time, and I'm going to put it as R hat over R squared and dq, and integrate over all surfaces. Yeah? This becomes the integral, and the small charge dq, and then you integrate it. Now, like I said, there could be line charges, there could be surface charges and isolated points. So let me write it all together and show you how that expression might look. So, first of all, there's this guy we just talked about. Because, again, you might have isolated charges. Then you might have line charges. So please pay attention. There's K R hat over R squared. A line charge. What I want to do is, this is dq. I want to define a density, linear charge density, and I'll call it lambda. Then, if it's a line charge, it becomes lambda dl. Does that make sense? Because suppose this length is dl. What is lambda? Well, charge per unit length. So I can write it this way, except this integration is over sources. So I'm going to put a prime to indicate that. We'll see what that means when we do a problem. Yeah? It is not altogether wrong for you to come, not watch the video, come and watch the next class, and I do a slightly complicated problem, but I'll do all the notation correctly, and then you can go back and watch the videos. Okay? Right, this is for line charges, and what if you have a surface charge density? What's the notation for surface charge? Sigma. And sigma dA, again, putting a prime over here. So this is just random charges floating about. This is line charges floating about. These are sort of charge sheets, maybe a capacitor. Okay, this one. And the last one would be just bulk volume charges. I'm running out of space. Plus K R hat over R squared rho d tau prime. So let me define all of them. Lambda equals dq over dl, linear charge density. Sigma is dq or dl prime, dA prime, surface charge density, and rho is dq over d tau. Mind you, tau is volume for Griffiths. It's the volume charge density. And amount of chalk and time. Is that clear?
When you say something like d tau prime, and you're saying it's only over the source, if we had like, we're integrating a sphere, that means we're only integrating the sphere.
That's right, not the space around it. Yeah, yeah, that's exactly what I mean. If you have line charge, you're only integrating over the line of charges, not points in space. Yeah, that's exactly what I mean. So the problem I will do in class on Monday is this example. Why? This is too simple. It's a video. This is very tough. Homework. Kind of nice that way. No, it's not tougher. Yeah, but it's a sweet spot. Yeah. Okay.